All right. Hi. So we continue off our discussion of computer software, and in the second unit, which is unit 2, we essentially just going to contextualize this whole notion of computer software. So we want to gain a sense of the software that we typically find on the different categories of computer systems. Remember, we had a lengthy chart of things like server computers and supercomputers and embedded systems, right? And this is obviously, it's a no-brainer. It's something that we perhaps may be familiar with, but it's important we talk about it. And then I thought it would also be important for us to look at various examples of computer software, and then finally just look at the process that so-called programmers go through to create this software. So how is this software created exactly, right? All right, and again, I'll switch this off just because it might be a distraction. Right, so just start with, I have a few examples. So these are examples from devices that I personally use. So a screenshot here just shows an interface that I typically use to interact with a router that we use to connect to the internet at home. We have a broadband subscription with Microcomputers, which is an internet service provider, or ISP. And so the router itself is a really small device that fits on one's palm, actually, on my palm, actually. But it has software on it that one would typically use to try and troubleshoot whatever problems might exist in the event that there's a problem. If for instance, I'm unable to connect to the internet, or if I want to say disconnect a device that might be attached to my computer. Perhaps now would be a good time for me to just quickly showcase how this is done actually. So I will, I think I am connected to the internet. I just go to 192.168.0.1 and then boom, I have access to my router. And lo and behold, you notice that my Wi-Fi here is dead. The red here means it's not working, right? But the key thing here really is that I use computer software on the embedded device itself to be able to interact with the device. And then, I mean, if you are one of those people who uses, I guess, operating systems such as Microsoft Windows, for instance, you're probably familiar with the interface on the current slide, right? Again, really doesn't matter which operating system you could be using on your desktop computer, but key thing here is that you interact with the machine, or you interact, or you tell the computer what to do by actually launching specific applications on your computer, right? Some interface here associated with a Linux-like operating system, which is Ubuntu. Again, it might look different from what you otherwise see on a Windows machine, but the idea is the same, right? You have access to a whole range of software applications, right? And you can install additional applications, you can uninstall applications when the need arises, right? And of course, if we're to look at the range of applications associated with our case study device, which is the Maono tablet, lo and behold, this is the interface that you'll be presented with, right? And you notice that in all these different instances, these examples that I was walking us through, the device would typically have so-called operating system that you use, or that directly interacts with the computer hardware. And we have a discussion of what an operating system is and what sort of function, what key functions it performs on behalf of the end user shortly. If I'm guessing most of us have smartphones, but if you look at smartphones or indeed feature phones, you typically have a broad range of applications that you use to interact with that particular device. So these two screenshots here are coming from my smartphone, which runs off all of these three screenshots actually. It runs a fork of Android Cortex GNOS, and it's version 9.0.6. My phone is the OnePlus 3T. You notice that depending on what I want to use the the phone for or the smartphone for, I could choose to access one of the installed apps, right? Or I could make use of the applications that come pre-installed on the smartphone itself. So these would be key applications that enable you to make calls, for instance, or send SMSs. In certain instances, there are applications that you access remotely. So applications that are associated with the mobile network operator that you would be with. So in this case, I believe I was accessing a service provided by MTN. So I'll just press *1 or *111#, and then I have access to this USSD menu here that I would use to interact with that piece of software. Right? We'll discuss all of these things, but you notice that in all these different instances, this application is being accessed remotely. It's not like it's installed on my machine, but I'm able to access it using my phone. Right? So the microcomputers, but the same goes for so-called server computers. Really, it doesn't matter which computer system you're looking at. So in this case, I was just doing a listing of installed applications on a remote server that we have access to. It's a list server, the one that is used to host the departmental web server. It's also used to host the DC server, so the one that you use to actually share resources when you're on campus. And I guess a key thing I wanted to mention here is, unlike these previous screenshots I was showcasing for the Maono tablet and for my laptop in this case, which has Ubuntu, and my phone, you notice that because I access this machine remotely, I'm actually using a terminal, which in itself is a piece of software to actually remotely log in into the server and list the software packages that are installed on that particular server. Right. All right. Hopefully that gives you an idea of the range of, I guess, software that you find on the different types of computer systems. Lo and behold, I don't have access to a supercomputer, so I can't showcase what tools you'd potentially find on supercomputers. But I suppose you could easily look that up online. All right. So in terms of examples, again, I know that it's a no-brainer. It's something that perhaps everybody is already familiar with, but I just thought it was important that we talk about some of these examples of computer software, right? If you think about it, these things that we are calling computer software, they just help us transmit data fundamentally, right? What's this data that is being transmitted? The data that would have been processed and presented to end users as an output by this computer system. Right, so this screenshot here, example software tools that we're probably familiar with is Facebook. Right? I don't know about you, but I log into Facebook because I want to see updates from my friends and family, because I want to read up on important news items that are being shared by the different important pages that I'm subscribed to. Could be a Ministry of Health, or it could be movie TV page, for instance. What I'm accessing is data, information, right? It really doesn't matter what sort of application you could be using. It could be Facebook, it could be Twitter, it could be Instagram, but fundamentally what you're doing is you're consuming information. You could really classify these as being, you could also classify them as being tools that facilitate communication amongst users. It doesn't matter. There's more though, right? There's examples like emailing clients that we use to access emails, for instance, right? The famous Gmail, for instance. In certain instances, you might also find yourself using productivity tools like calendar applications or project management tools like Trello, for instance. Right? These are all different types of computer software that we use to interact with hardware, right? And the hardware performs the action depending on what sort of feature accessing associated with that particular computer software. Examples closer to home include so-called SIS, or Student Information System, the learning management system that we use, which is Moodle, or it runs off Moodle. And really, you notice that depending on what you're using the computer system for, you might end up installing or accessing a wide range of computer software, right? So it doesn't necessarily mean that you would perhaps have the same sort of apps that I have installed on my phone, just because we have different use cases, right? I wonder how many of you have the CPU info application installed on your phone, or the calendar app. Who knows, right? All right. But in terms of how this so-called software is implemented, how it gets to be created, it's an important discussion, although this is covered in great depth at second year when you look at Introduction to Programming, but it's something that is important to discuss to help understand subsequent lecture series that we're going to discuss. So typically this so-called software is created by human beings, people like you and me. And I guess increasingly there are probably AIs that create software. Who knows, right? Should look into that. But these things we are calling computer software are actually written by programmers using programming languages, which are themselves a form of software, right? It's like one of those chicken and egg problems. So a programming language, which is a piece of software, is used by a programmer to create software. So if I wanted to create a piece of software that enables first-year students to be able to log in a problem that they might have and submit it, for instance, rather than sending email, I would have to use a programming language to write that piece of software. Once I write that piece of software, I would then be able to install it on my computer and be able to use it. Of course, in certain instances, you don't necessarily have to explicitly install the piece of software. All you have to do is just execute it or run it. So these things that we are calling programming languages, the software that we use to write software, they come in different shapes and forms, right? But fundamentally, they are classified into low-level programming languages and high-level programming languages, right? And it's usually the case that programmers will typically use a high-level programming language, just because it's more intuitive, right? And really, this whole notion of high-level programming languages versus low-level programming languages is essentially tied to this notion of abstraction. A high-level programming language has a higher level of abstraction in comparison to a low-level programming language. And really what we're referring to by a high level of abstraction and low level of abstraction is relative to the native language used by the computer system, right? So essentially, I mean, if you look at the native system as the native language for that computer system as being tied to binary code or machine code, what we're saying is that a high-level programming language will have a high level of abstraction of the machine code in comparison to a low-level language, right? And really, it all boils down to how easy it is for you to interpret the language, right? So it's much easier for a human being to interpret a high-level programming language or to be able to understand the high-level programming language rather than a low-level programming language, right? So the takeaway point here is just abstraction. And so what this screenshot here is showing is it's showing the same piece of software or piece of code being presented using a high-level programming language, in this case C, and using a low-level programming language or two low-level programming languages, assembly language or MIPS, and machine code, right? So you immediately notice here that you can understand things like swap, right? This is in English, by the way. So words like temp, for instance, it's much easier for you to understand these things rather than this stream of ones and zeros, for instance, or things like LW and add and JR, right? You'd only be able to understand what this is if you actually thoroughly studied MIPS, which we do once we look at the computer architecture component of the course, right? So again, takeaway point here is that when we're referring to high-level programming languages and low-level programming languages, we are referring to the abstraction, right, associated with the native language that the computer system uses. It has nothing to do with how powerful the language is, right? Just because we're saying it's a high-level programming language doesn't necessarily mean that it's much more powerful than the low-level programming language. It's essentially tied to abstraction. This piece of code does the same thing as this piece of, or this stream of ones and zeros here. And so just to, I guess, take us back to our discussion of the historical overview or historical perspective of computer systems, you remember that we went through a process of identifying which sort of languages were used in the various computer generations. I just thought it would be important for us to talk about this, not just used, but in which generation these different programming languages were introduced, right? So a reminder that obvious first generation computer systems were primarily programmed using machine code. So the software that was used on first generation computer systems made use of so-called machine code, so binary code, ones and zeros, right? And then as we go high up the generations here, you notice that we see an introduction of assembly language in second generation, and I do believe some high-level programming languages like COBOL, for instance, and Fortran were introduced in the second generation. But more importantly, notice that third, fourth, and fifth generations all make use of so-called high-level programming languages. So languages like Python and Java and Perl, for instance. Right. I also thought it would be important to distinguish programming languages associated with the 5 computer generations and the generations within which these different programming languages are classified into, right? So if you read up online, you probably come across literature that will point at the fact that the different programming languages that we have can be clustered into their own generations. So we have first generation programming languages, second generation programming languages, third generation all the way up to 5G, which are fifth generation programming languages. Now, this is different from languages that we're referring to in this particular lecture slide, right? Essentially, a way of thinking about the generations associated with the programming languages is to look at, again, the abstraction, how closer you are to the native computer system language, right? And really, this is best viewed from the perspective of the fundamental building blocks that are used in that particular programming language. So for first generation programming languages, you're essentially working with bits, right? So binaries, ones and zeros, right? Or binary code. And then as you go high up the various generations, if you look at second generation programming languages, you are essentially looking at individual instructions. And then for third generation programming languages, you're looking at more abstract operations. So if you have to do a comparison between looping constructs created using a second generation language like MIPS assembler, for instance, and compare it with looping constructs associated with programming language such as Java, you notice fundamental differences there, right? So building blocks is a key thing here. And you notice that as you go high up the hierarchy here, you have things loosely associated with domain objects for fourth generation languages. And I guess a classic example here is structured query language. And then finally in fifth generation languages, you're really looking at overall goals associated with computer program that you might be interested in creating, right? These are mostly used, and I'll be the first to say I haven't really worked with any fifth generation programming language, but these are mostly used for AI-centric problems, essentially. So examples can be found online, but I guess common example you find is a language called Mercury. All right, I just thought again I'd draw our attention to specific examples associated with these high-level programming languages. On this particular screenshot here, or slide, I have screenshots for two types of languages, right? This is JavaScript and this is Python. And you notice that this simple program really is doing nothing more than just printing the first 10 natural numbers. And you notice that printing the first 10 natural numbers is quite easy here, right? All I need is 3 lines of code for me to be able to print the first 10 natural numbers. I don't know if 0 is a natural number, but that's besides the point. But you immediately notice that the building blocks that I'm working with here are readable, right? So things like for, var, number, equals. If you've done maths, you know what equals is. If you've done maths, you know what this greater or equal to sign means, right? This is besides the point here. But there's a whole range of programming languages that are available out there, hundreds of them. I dare you to just do a simple search for list of high-level programming languages. You'd be amazed as to how many there are out there, right? Maybe now would be a good time to just do a simple demo here, and I'll use JavaScript here to say I want to print the first 10 natural numbers. Notice that it's as easy as me just saying I want to print a number beginning 0, and I want this number to be greater or equal to 10, and I want to increment this number every time I print it. And then I want to log the number, right? And then I'll print it out. So you see how easy it is. So I just use JavaScript to do that. If I wanted to do this in Python, you notice that it's even much easier in Python. I'll just say for number in range 10 or 11 in this case, just say print number, right? So I do this in just essentially 2 lines of code. Easy. Just if you don't understand any of this, the point is not for you to learn or know how to write a computer program, but rather to gain an appreciation of the fact that the building blocks that you make use of are things that are readable, right? They're human readable. Getting excited here. I can also do this using shell script, or just say for number in sequence 0 to 10, I'll just say do echo number, right? Done. So I'm just showcasing examples using different high-level languages. I use JavaScript, Python, and Bash, right? All right. But in comparison to low-level languages such as MIPS assembler, for instance, so assembly language programs and machine code, you notice that if you look at assembly language, these building blocks are not immediately intuitive. For you to be able to understand what BGT is, what LI is, you'd need to read the manual associated with this particular assembly language that is on the slide, right, which is MIPS assembler, right? And the reason why these mnemonics, or the building blocks, the reason why they're not human readable is they provide a direct mapping between these individual instructions, so these lines that you're seeing here, to the actual binary code that is executed by the computer system, right? So low-level language versus high-level language, low-level programming languages. But you notice that even as you look at the so-called low-level programming languages, you immediately realize that there's still a difference, right? So this screenshot here is showcasing a mapping between what you're seeing on the far left of the screenshot is a hexadecimal representation of the machine code, which is, for MIPS, it's represented using 32 bits, but it is presented alongside the assembly instruction, right, associated with this particular program. Again, this program really that you're seeing on the screenshot does the same thing as these programs that I was showcasing, right? It's the same exact thing, right? Maybe another example would be good here. So if I was to fire up this MIPS simulator here, and if I load and I hope I get to the point, okay, assembler. If I load this program, right, and the program that I just loaded, by the way, is the same one that you're seeing on the screenshot. So if I was to quickly navigate to the folder that has that particular program, you will notice that, just quickly order them by, there we go. So immediately notice that it's similar to what is actually in the slides, right? So this program does nothing more than print the first 10 natural numbers, right? In case people want proof here, so I've loaded the program. If I execute it, you notice that this console prints number 0 all the way up to 10. So same thing that I'm able to do using Bash, using Python, and using JavaScript, using Node.js there. I can do with assembler, right? But in case you haven't noticed, you immediately realize that as you abstract the native language even more, the number of lines of code that you need to do the same thing is significantly reduced, right? So for both Python and Java in this case, all I need is 2 or 3 lines of code. But if you look at the number of lines of code that I need to print 10 natural numbers, if I write the program in MIPS assembler, you realize that I need 29 lines of code, right? Because the level of abstraction is much lower here, okay? Hopefully that makes sense. It gets even better though. So what the computer actually works with is not the assembly language instructions, but rather the ones and zeros, the binary, right? The streams of ones and zeros, the binary code. And actually you soon get an appreciation. We're abstracting all of this, which is why we're saying the computer executes ones and zeros, but really fundamentally, what a computer actually works with is flow of current, right? So a 0 would represent maybe a low voltage of electricity, and a high is a high voltage of electricity. A 1, sorry, is a high voltage of electricity. Or perhaps in certain instances, a 0 will mean there's no flow of electricity, and a 1, it means that there's flow of electricity, right? Through a circuitry, right? So again, we are saying it's ones and zeros because we're abstracting all of this, but I assure you very soon all of this will become clear. All right, so still on implementation of so-called software, something else that is really important to discuss here is this idea that typically software is created for a particular hardware architecture and operating system. So software that is meant for Android cannot easily be installed and executed on, let's say, Linux or a Windows machine. Although, I mean, these days, you could use emulators to be able to execute Android applications on, let's say, a Windows operating system or a Linux operating system, right? But it doesn't take away the fact that software is typically implemented for a specific hardware and for specific operating systems, right? I guess to give you an example as well, I have found myself in the past, I found myself in situations where I need to run Windows applications on my computer. And so one of the ways I can do that is I can perhaps install an emulator, right? So something similar to VirtualBox, for instance, that allows you to install a Windows operating system within it, right? So it's a hypervisor. Alternatively, there's software for Linux such as Wine, for instance, that allows me to run Windows applications. There's a really important application called Publish or Perish that only has a Windows version, and the only way I can run it on Linux, if I don't use VirtualBox, is by using an application called Wine, right? And in fact, if you look at Internet Explorer 8 here, I can run Internet Explorer 8 on my Linux machine or Ubuntu here because I have Wine, right? All right. But key takeaway point here is software is typically designed and implemented for specific hardware architectures and for specific operating systems. It might not be possible for you to install 64-bit software on a 32-bit hardware architecture, for instance. All right. And still on how computer software is implemented, in 2010, which is Introduction to Programming Languages, or Introduction to Programming, or rather, you'll be introduced to this whole notion of the software development lifecycle. So typically, software programmers will, before they actually start writing application software, they'll typically have to collect requirements to be able to ascertain what sort of features that piece of software is supposed to exhibit, after which they go through a design phase where they come up with a high-level design of the software that they wish to implement. And then using this design, they will actually write the actual instructions or program instructions associated with a piece of software. What they're doing here is mapping on the design artifacts with the actual software code, right? And again, like as earlier mentioned, the program code will typically be written using high-level programming language. In the process, as you're writing these program instructions or the software tools that you've designed, you go through a process of trying to make sure that it works as expected, right? So you test the software. And then finally, you go through this process of evolution where perhaps you might have to fix bugs, right? Or develop patches, for instance. This is where those system updates for Windows come in, right? It's all part of the evolution process. So essentially, it's an incremental process or a cyclic process where you collect requirements, you design the piece of software, implement it, test, and then you go through the evolution process. You repeat or you loop, right? Takeaway point is just trying to highlight the process that programmers go through when writing software. Collect requirements, design, implement, test, and then loop. Right, so to help emphasize this whole notion of software being implemented for specific hardware and operating system, I thought it would be nice for us to showcase an example. There's a very popular open freely available and open source Office package called LibreOffice. I have it installed on my machine myself, right? So there are a number of tools associated with that software package. If you go to the download page of LibreOffice, you immediately notice that you're given a provision where you get to select which operating system you want to download the software for, right? So if you were installing LibreOffice on Windows, you'd have to select Windows. If you downloaded a Linux version and attempted to install it on Windows, you'd not be successful, right? Even better, there's an option where you get to specify the hardware architecture where you want to install this piece of software, right? So in my case, my computer, this Lenovo Ideapad 320, is 64-bit architecture, right? So which is why I had to download this x86 64. Right? Suffice to say that it's usually the case that if you have a 64-bit hardware architecture, you can install 32-bit software and 64-bit software, but the inverse is not true, right? So if you have a 2-bit hardware architecture, you cannot install 64-bit software. All this will make sense very soon. We have a thorough discussion of hardware architectures once we look at the CPU, for instance, central processing unit, as part of our discussion of the von Neumann architecture, the von Neumann model, right? So again, you look at the different options here. If you have a Mac OS, you choose Mac. If you have Linux, you choose Linux. If it's 64-bit, you choose that. If it's 32-bit, you choose that. If it's running on an Ubuntu operating system, you download the Debian package. If you are using a distro such as Red Hat, I suppose you download the RPM package, right? So I thought it would be important to highlight the fact that, or to showcase an example of why it's important for you to choose or why software is designed, or examples on why software is designed for specific hardware architectures and operating systems. Right. So this whole notion of software really is best viewed from the perspective of the different categories of software out there. And fundamentally, software is grouped into application software and system software, right? We have a lengthy discussion of what application software is and what system software is and the different subcategories. But fundamentally, application software is one that we mostly interact with when we're using when you're using the average computer system. So these would be things like productivity software tools such as Microsoft Word, for instance, or spreadsheet applications like Microsoft Excel, right? And system software is really the more system level tools and services that directly interface with the hardware. So things like the operating system. Right. But we have a lengthy chart about application software and system software. But just to recap this particular unit, we looked at really just some simple examples of the sort of software applications you can find on the different range of computer systems, but we restricted our examples to microcomputers and server computers, right? And then we looked at some examples of software tools that most of us use, and then briefly went through a discussion of the design and implementation process that you'd otherwise have to go through for you to create these things we are calling computer software, right? And then finally, we set the stage for upcoming discussion of the broad categories associated with computer software, which is application software and system software. So hopefully this all makes sense. I'll see you in the next unit or section where we get to look at application software. Thank you.